Good afternoon and welcome to our 24th Jazz Sessions. This one's going to be a little bit for the science geeks. It's not for general writers, although anybody could make use of the information, but it's particularly designed for science geeks in mind. Living and dying in free fall and spin gravity. Two topics that can be very important when you write hard science fiction like me, or even more general science fiction. But first, of course, we have our little video.
Why don't you let me fix you some of this new Mococo drink? All natural cocoa beans from the upper slopes of Mountain Nicaragua, no artificial sweeteners.
What the hell are you talking about? Who are you talking to?
I've tasted other cocos. This is the best.
If you're not familiar with The Truman Show, it is the one Jim Carrey movie that I absolutely love and never miss. The premise is that his whole life he's actually been on a reality TV show without anybody telling him. Everyone else in the show are actors, and that includes paid placement for products within their television show because they do need to pay the bills and keep the lights on, which is, of course, the theme of paying it forward. And this week we have paying it forward just a little bit different because we are paying for the soup. And we are going to talk about my Making Story Models book, the one on the right, as usual, which is the book that covers the material we spent a month on here in the jazz sessions. But I want to talk about the one on the left right now. Win in the End is an anthology of short fiction put together primarily people from the Superstars Writing Seminar to help out one of our fellow tribe members in a bit of need. And this is a book that we put together and we have been promoting to all of our audiences to try to do some good in terms of fundraising by doing good in terms of fiction. And it includes quite a lineup. Sam Knight organized the project with editing by Leslie Bridgewater. And we have stories from this lineup of must be 20 different people, most of whom I have met in my writing career at one point or another and have had a chance to work with, all out here trying to help a friend and tell a good story in the process, we hope. And if you like my short story, Today I Am Paul, if you like the novel that came from that, Today I Am Carrie, this is the only place to get the newest Carrie story, Today We Escape. So if you'd like to read that story and if you'd like to help a friend, this is the place to do it. And this is our QR code for that. So as Edith Keeler said in Star Trek, it's time to pay for the soup. But sometimes it's not about paying for my soup. Sometimes it's about helping out. For those who haven't seen one of the jazz sessions before, of course, our emphasis is on tools, not rules. Anybody telling you rules for writing is either naive or trying to sell you something. There are no rules beyond you must write. There are many useful tools, but as William Goldman, author of, among many things, The Princess Bride, both the book and the movie, as he told us, nobody knows anything. He was talking about the movie business, but it's all creative arts. Not one person in the field knows for certainty what's going to work. Anyone who gives you a rule, I will find you a dozen books that succeeded while breaking it, and I will find you a dozen books that followed that rule to the letter, thinking they'd found the golden ticket to success and went nowhere. Learn tools, don't rely on rules. Even if someone like me calls it a rule, because it's easy to call things rules as a shorthand, it's still a tool. All right, so this week, for the science geeks, we're going to be talking about science-y stuff. And if you feel like, hey, I don't care about getting the science right, it's science fiction, duh, that's okay. You write what you want to write. but you may be in the wrong class then, because I'm going to be talking about getting it right and why that matters to me, but might not to you. There's definitely a market for getting it right. The Martian was, in its first release on Kindle, 35,000 copies in 3 months, $10,000 if I estimated what his royalty rate was, because he was billing the book at first at 99 cents, and so that would be the 30% royalty rate. Was the #1 in Amazon science fiction, which then got sold the audio rights to Podium Publishing and the print rights to Crown for $100,000. Only the print rights. They wanted to buy all rights, and he said, why? And his agent said, why? We're already making money as fast as we can on the ebook. You don't need the ebook rights. And Crown said, well, then we're not interested. And then the agent said, okay, then we're not interested. And Crown said, huh? You're supposed to fold when we do that. It's like, no, somebody else will want them. So Crown bought the print rights. Was a New York Times hardcover bestseller for 4 weeks. Trade paperback bestseller for 76 weeks, including 19 weeks as the #1. Turned into a film that grossed $630 million. And this is an old slide. It's probably gone up since then. And I described this book and this movie as they made it for me, and you're all allowed to watch too. They made it for me because I love the hard science about this. I love all the nuts and bolts of the science, and yet he got it wrong. The fundamental premise of the whole book, the horrible storm on Mars that's going to blow over the spaceship so they have to evacuate right away, cannot happen. Mars's atmosphere is so thin that you might get blinding dust storms and sandstorms. You might not be able to see where you're going, but the wind hitting you fast, hitting you at hundreds of miles an hour, is still so thin that it'd be like being slapped with tissue paper. The whole premise of the book and the movie falls apart. But that didn't stop it making $630 million as a movie. Gravity, as a movie, grossed $723 million. Has a 96% fresh on Rotten Tomatoes. Got 7 Academy Awards. And Buzz Aldrin just raved about the book because of how realistic it was and how much it felt to him like actually being there. And he's one of the few people who's actually been there. And yet, an awful lot of NASA people did not like this movie because it gets so many things wrong in terms of the science. Fundamentally, basically wrong, including things that the director looked at and said, I know that's wrong, but if I don't do that, my story doesn't have any excitement, so I'm going to do it wrong intentionally. But it made $723 million. On the other hand, this one, Europa Report, if you've even heard of it, was so absolutely realistic in every last little detail. Praise for it by Gizmodo and Space.com. Just amazing. And it grossed 126,000, not million, thousand. So apparently getting it right is not enough to get it an audience. And then on the flip side of that, we have Star Trek, where the science is laughably bad more often than not. Horribly, laughably bad. And they have made $10.9 billion off of it. And this is from, I think the slide was from 2019. So you can probably add a couple billion onto that now. So apparently getting it right is not nearly as important as getting an audience. But some people, their audience is, they like to get it right. And some people, as writers, i.e. me, like to get it right. So are you trying to write it for real or for readers? And I talked about this in an earlier jazz session, the concept of the sweet spot. If you look at this curve as representing all the different people in the audience and how much they know the actual field that your science is. On the left, we have people who are just here for explosions, just here for chase scenes, fight scenes. They don't care. On the far right, in the blue, you have the experts, real experts in the field, who can't even agree with each other. Watch three quantum physicists discuss the Copenhagen interpretation versus the many worlds interpretation of quantum mechanics. And they will argue all day about it. So whichever one you do, half of them are going to say it's wrong. In the green, that middle ground are people who just like sort of the sciencey talk. They want the right buzzwords and stuff, but it's all they really care about. The sweet spot is that yellow zone. Educated lay people who kind of know the science, but not enough to do it professionally. I like to aim for satisfying them. And I'm going to be giving a talk that tries to satisfy them. I'm going to be trying to look for good, which is the items on the left, not bad on the items on the right. So good is descriptions, experiences, consequences, challenges, discoveries, debates, popular science level theory, things that are tied to the science, but tied to the science to make the characters struggle and make the plot advance. On the bad side, we don't need math and charts and citations, except I can show you books that have done all three. We don't need flow charts, but I'm tempted to do one sometime. We don't need the actual chemical formula and recipes, although you'll find recipes in some cozy mysteries that are actually cozy mysteries tied to cooks and chefs and so on. We don't need PhD level theory, and we don't need the as you know, Bob, way of exposition. We need the amount of science that pushes things forward, not drags things down. And then I'm going to throw math at you anyway, because it's a little important, not a lot important, but a little important when we're dealing with gravity. Gravity is the force that pulls things to the ground. Or is it? One of the things we learned from Einstein is gravity is not a force. In modern physics, gravity is not something reaching out and pulling on that apple or the moon or you. It is the weight of the earth actually bending space. And this picture is a dramatic representation because the actual bend is in 4 space. I suppose if you're going to talk about time space, it's 5 space. It's not in length or width or height, and it's not in time. It's in a direction perpendicular to all of the above, that an object makes a bulge in that space. And when something tries to go in a straight line through that space, the mass of the object pulls it into a curve. And so gravity is not a force in the sense of you pushing on a baby stroller is a force, or the sense that you trying to pull 2 magnets apart is a force. It is a different sort of thing that is mathematically equivalent to a force in almost all cases. But there are edge cases where it is not a force. And so as your physics goes higher and higher, you start reaching cases where the curvature of the space actually matters. But you can think of it as a force for the most part. The important thing, hello. The important thing is it pulls objects toward each other. And if you're really going to think about the science and think about the way it might affect a story, all objects have gravity to all other objects. As I sit here, my computer is pulling towards it with gravity, and I'm pulling it towards me. Our gravity just happens to be a lot smaller than the Earth's gravity. But everything pulls to everything. There is a gravity between you and me, wherever you are in Utah or Arkansas or wherever. I am hitting you with a little bit of gravitic pull towards Michigan and vice versa. But we're so far apart and we're so small that no one will ever measure that. And that's where we get into the math. Sorry to throw math into this, but there is a basic formula for what the force is of gravity between two objects. And that force is a universal gravity constant, big G, times the mass of one object, my mass, times the mass of the other object, your mass, divided by the square of the distance between us. And on a planetary scale, my mass and your mass multiplied together comes up to teeny tiny. And our distance between us comes up to thousands of miles, or at least hundreds of miles. And so we're taking a very tiny number, dividing by a relatively big number, relatively big compared to us, not compared to planets, and then multiplying by this universal constant G, which is a tiny little number, ending up with something that is so small that we could not measure it, but it's there. Or if you think in terms of the dimple in space-time, the size of the dimple depends on the mass of the object, and you and I have so little mass that the dimple we create in space-time is unnoticeable. But we are creating a dimple. Now, something I want to point out, if F equals gm1m2 over r squared is the force of gravity acting on us, we also know from other Newton, gee, I'm just throwing so much math in here, that force equals mass times acceleration. And therefore, the force is the force. The force of gravity is mass times acceleration. So if we take your mass being pulled by the Earth as m2a equals the force from gravity is g m1 m2 over r squared, and we divide the m2's out from there, we get that your acceleration is g times the mass of the Earth divided by r squared. And notice what's no longer part of the equation at all. It's your mass. And this is one of the most fundamental things that I still see people get wrong in some science fiction stories. They still think that heavier things fall faster. And what the math says, and Galileo worked out, is no. The Earth pulls every object at the same rate. It doesn't matter if it's heavy, it doesn't matter if it's light. It matters if there's air resistance. The classic feather versus cannonball, the air resistance on a feather is huge. The air resistance on a cannonball is tiny, insignificant. But if it weren't for that, they're going to land at the same time.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
So that, of course, was an Apollo mission where they wanted to do a little science lesson on the moon, where there's essentially no atmosphere. We could quibble about the few molecules that are there, but there was no air resistance to stop the feather, and the feather and the hammer fell at the same rate. So there's one thing, even if you're not doing hard science fiction, don't make wrong science fiction. All objects without air resistance or some other sort of thing holding them up, like, I don't know, magnetic fields or something, they will fall at the same rate. And gravity, this is another classic example that's not quite right. Gravity affects everything with mass and everything else. Because if we go back to this picture, of force space bent by mass, everything in force space desperately wants to travel in a straight line, but because the space is bent, it curves. That includes light. Light wants to travel in a straight line, but it enters this curved space and bends around. And so light itself can be bent by gravity. And that's one of the reasons why when they say gravity is a force, one of the reasons that is wrong is that there's no force acting on the light. There's only the curvature. And what this means is one thing which was only theoretical until we've started to be able to slowly observe it, is that the definition of a black hole is something so dense, so much bending of the space-time, that even light can't get out. The bend is too steep. Light that would try to get out just ends up falling back into the hole. And the other is a cool experience, which we see on occasion, where an object, it might be Jupiter, it might be something more distant, like a galaxy, passes in front of another object, and we can see the other object because the light bends around the object that's in front. And so we can see that when a Jupiter passes in front of a particular star, we will still see that star, but we won't see it where Jupiter is. We'll see it off to the side because the light that was passing by Jupiter gets bent around and comes back and points right at us. So yes, gravity affects everything with mass, but it also affects everything without mass. Anything in motion in space-time, which is everything, nothing is standing still, is going to be affected by gravity. It's just going to be more noticeable because the light is traveling so fast it's in and out of the gravitational field most of the time before it even notices, whereas you and I, traveling at our normal speeds, get a lot more time to get pulled. Something to keep in mind, which is, again, something that is often done wrong in science fiction stories, the difference between weight and mass. Mass is how much stuff you have. Weight is how much stuff, how much force the gravity is pulling on you with. And in our world, in day-to-day life, they are very close to the same thing. Pounds, then you are weighing roughly 220 newtons. If is the measure of force in the metric system. But if I take that 100 pounds, that 220 newtons on Earth, and put it up into orbit, the weight will be practically nothing, but the mass won't change. And if I put it onto Jupiter, besides the fact that there's no solid surface on Jupiter, so you're going to end up falling down into the gas giant. But before you fall, if you were on a platform there and we held that platform aloft somehow, your mass would not change. Your weight would be crushing. And this becomes important because people are used to the idea that heavy means it is something I have to work hard to move, and if it falls on me, it will hurt me. And if it crashes into me because it's a heavy car, it will hurt me. And then they'll get into space where mass hasn't changed, but weight has. And so this thing is weightless, so it's harmless. It's like, well, no, sorry, more math. The kinetic energy of that thing hitting you is mv squared, mass times the square of its velocity. There's no F in there. There's no G in there. The kinetic energy doesn't change just because you're out where there's almost no gravity. And so it can still smash into you and crush you. And your ability to move it, well, it's so light, I can just push it out of the way. It's like your ability to move it, force equals mass times acceleration. So acceleration equals force divided by mass. So the amount of force you can push doesn't change. So when you take your force divided by the mass of that car, you still can't push it out of the way. What you could do, on the other hand, is gently start it moving. If you've ever had to push a car on a road, you know that if you push long enough, you get it rolling. But the friction of the tires can make it slow back down. And the hill that you're trying to push it up can make it slow back down. Out in space, no friction, no hill, other than minor differences in gravity. So you can push any car. You can, as a measurable amount, but a very negligible amount, you can push any spaceship. You can push a space station. It's going to push you more than it, but you can actually make a measurable difference with your human muscle that will be just enough so you could say, yes, it happened, but not enough to make a practical difference. Because you are applying a force to a mass, and there's no friction to stop it. So it will budge. You're going to budge a whole lot more. Another thing to keep in mind with gravity is tidal effects. The idea of a tide is like, wait, what, there's oceans? Well, yes, there are oceans, but not necessarily out in space. But the cause of the tides turns out to be gravity. The tides have to do with the fact that the moon and the sun are pulling on the ocean, and they're pulling on the ocean across the entire span of the Earth, which the span of the Earth by itself is 8,000 miles across, and the ocean is riding on that 8,000 mile surface. And remember that the bottom line of that equation, oh, it's right here. The bottom line of that equation is divided by r squared. Now, to you and me, r squared from here to Utah isn't that big. But across the span of the Earth, from one side to the other, to have a difference in distance of 8,000 miles means that the water closest to the moon is being pulled a little harder than the water farthest from the moon. And on top of that, it has a long time to pull. If you and I were at our current distance out in space for probably tens of thousands of years, our gravity might be enough to eventually pull us together. The moon doesn't need that long. It is pulling constantly on the ocean all day long, all night long, but the Earth is rotating underneath it. And so this causes tides to come in as the bulge follows the moon and go out as the bulge leaves. And there's a lesser tide from the sun also pulling. So if you get the moon and the sun roughly on the same side, you get a higher tide. If you have them on roughly opposite sides, you get a much lower tide, and everywhere in between. So that's cool. What's it got to do with space? Well, tidal effects apply everywhere. Let's talk about the classic example of falling into a black hole. There are all sorts of wild speculative stories about what happens when we fall into a black hole. And for the most part, I'm going to call them all wishful thinking. That mostly what happens when you fall into a black hole is you go dead. Interestingly enough, and we're getting off the topic of gravity and getting into relativity, which is, of course, related to gravity. But interestingly enough, relativity tells us that your time slows as you fall into the black hole. So, and what's weird is my time doesn't. So as I'm watching you fall, I am seeing time going at quote-unquote normal speed. You are seeing time going at normal speed, but your normal speed that I watch gets slower and slower and slower to the point where you will never actually reach that black hole in what I can observe. But you are going to reach that black hole in a relatively short time in your observed time frame. But before that, you are probably going to get this technical term that they call spaghettification, meaning you're pulled into thin little molecular strands of spaghetti because your feet are closer to the black hole than your head, or maybe it's your nose is closer than the back of your head, or something like that. Whatever way you're oriented, part of you is much, much closer to the black hole than the others. And you say, much closer at 6 feet. Yes, but again, just like the tides of the Earth, one side is closer than the other. If we look at the mass of the black hole, and the mass of the black hole is so steep that we get a significant gradient curve between your feet and your head, significant enough that it will literally tear your atoms apart. But from my perspective, that's not going to happen for the next 1 or 2 years because you're just never quite going to reach that black hole. From your perspective, it's going to happen fast, and you're lucky that you probably won't have time to feel it because I cannot imagine much more painful than spaghettification. So gravity does weird stuff sometimes. And we already saw the little video. So how strong is gravity? And the answer turns out to be not really very. Because that G in the equation is a significantly tiny number. 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. Math. The important part in there is the 10 to the minus 11. 10 to the minus 11, whatever is the actual math going on, tells us that this is a really tiny effect. And if you're into physics, you're probably aware of the 4 forces. Gravity being one of the fundamental forces of the universe. The weak nuclear force is the force that particles in the atom use for pushing each other apart. Protons trying to push each other away, electrons trying to push each other away. It's 10 to the 32 times the strength of gravity. It's huge. Electromagnetism, which is what powers our society and which makes magnets pull apart and hard to pull apart and so on, 10 to the 36 times. And the strong nuclear force that holds the nucleus of an atom together and says, hey, you protons, I know you want to push each other apart because they're both positive and 2 positives don't like each other, but I'm the strong force and I'm 10 to the 38 times as strong as gravity. So I'm going to hold you together. So gravity is really, really weak, but it's cumulative over mass, it's cumulative over time, and it has a bigger net effect in our day-to-day lives, especially if we're looking at that mass of the Earth, because that M1, the mass that we're getting pulled by, is almost 6 times the 24th kilograms. So even though gravity on average is much smaller than the other forces, it is bigger cumulatively. Especially because, again, if we look at electromagnetism as an example, we have positive and negative charges that kind of cancel each other out. There's nothing canceling out gravity. It's all cumulative. Any dent in that 4 space, in that 5 space, any dent in that is cumulative. So if you stand on the Earth's dent is a little bit bigger because of you. Yay, you're contributing to gravity. It holds us all here. And the radius of the Earth, 6,300 kilometers, is big, but not so big. If it were bigger, or if you are farther out, because it doesn't really matter the stuff, it matters how far you are out. So if you move farther away on your spaceship, the gravity goes down. But if you combine all those and do the math, this comes out to 9.8 meters per second squared. One of the most fundamental measures in physics, if you're doing any sort of practical work, is that is the average acceleration due to gravity on the Earth. and all sorts of ballistics equations and friction equations, all sorts of things factor that in. We call that little g, the one Earth gravity. And to give you a feel for what that's like, if you imagine opening a heavy door, gravity is generally like 7 to 15 times that. If you imagine braking a car, it's about half a gravity if you're just gently braking. If you stomp on the brakes, it's about a gravity. If you imagine standing under your bathroom shower, you are getting hit with something that's about 1/200th of a G. And of course, you have an intuitive feel for 1G because you carry your weight around all day. So you kind of have this feel of this is what normal is. If you move farther away, it goes down. Or if you go to a more massive planet, it goes up. Or a less massive planet, it goes down. Now, here's a terminology battle I expect to lose. I'm going to do it anyway for Marion. My friend Marion J. Dyson, who wrote the foreword to my book, The Last Dance, says, call it free fall. You don't call it zero gravity, especially don't call it zero gravity, and you don't call it microgravity, you call it free fall. And Marion was one of the first female flight controllers for NASA early in the Apollo program. So she's got much better credentials than me. If she wants to call it free fall, I'm going to call it free fall. Because remember that equation, G m1 m2 over r squared. As r gets bigger, gravity goes down, but it never goes to zero. You are always feeling some tiny pull of Earth's gravity, even if you're around another star. So tiny that you can't measure it? Yes. But you're still feeling it. There is still a dent in that space-time continuum somewhere out there. There is no upper limit on R. But when you are in orbit, you perceive zero gravity because you and everything around you are all falling at the same time, free falling. We'll talk about that a little bit further when we talk about orbits. So there is no real zero gravity. There is free fall. Microgravity could be an interesting term, but nobody has a formal definition of where the line is for micro. If you get far enough away from Earth, the gravity from Earth may be maybe 0.98 meters per second squared, 0.098, 0.000098. If you wanted to say that 1,000th of a G is microgravity, you would be sort of linguistically correct because micro is thousandth. But there's no formal definition for microgravity. So I'm going to tell you what Marion taught me, which is we're going to call it free fall. And you don't have to believe me. You do not have to listen. However, when you read my fiction, look really carefully. If you find the word zero gravity or microgravity in there, it will be the voice of a character. It will never be the voice of the narrator. Because I, as the narrator, have been schooled otherwise. Now, besides being one of the first female flight controllers, Marion is a very, very widely accomplished author. This is one of her books she did. She does a lot of children's and adult educational books, more children's, on space sciences. This is one she wrote about the construction of the space station. She has done science fiction. She has done poetry. She has done a biography, which is what it was like to be a woman coming up in the field at that time. She has done a pop-up book. And she has often co-authored with Buzz Aldrin on some of his general science education books. So she's got the credentials, and so I'm going to listen to her. So let's talk about what an orbit is. And this illustration is one of the more classic illustrations. I had to search online a bit to find this particular example one. But just think about what happens when you shoot a gun and you're holding to try to shoot as level as possible. Maybe you've got it on a tripod so your arm doesn't droop, and you're just trying to shoot as level as possible. Sooner or later, that bullet falls and hits the ground. And there's a mathematical equation to express this. We're not going to do any more math. I've already done more math than you ever wanted me to do. But now let's have a faster bullet. You've got more powder, you've got more efficient powder, whatever. It's a bullet going faster. It goes farther before it hits the ground. But notice that as it's going farther, the ground itself is dropping because the earth is round. And so as you go faster and faster out of that hypothetical gun, the amount you have to fall to hit the earth goes up until eventually you're essentially falling sideways so fast that you never hit the ground, that you're falling sideways at such a speed that the earth can't quite catch you. And maybe you come close. Maybe if this bullet keeps going around, it will be kind of really close to the earth, but if you've got it going fast enough, it will still zip by and come back around. So really, that's all an orbit is falling around the primary, the planet, the star, the moon, whatever, falling around it so fast that you won't ever quite hit the ground. You will just keep falling, hence the term free fall. And this is why it's not zero gravity. Even though you're not feeling any gravity in the space station, you are not feeling any gravity because the space station is falling at the same time you are. And if you drop your sandwich, the sandwich is falling at the same time you are. Everything is falling around the planet at the same speed and therefore never falls to the ground. There was an interesting reel I saw just yesterday, and I should have saved the address for it so that I could share it for you today. But it was a guy talking about why it seems like when a rocket takes off for space, it seems like they spend more time going across the sky than going straight up. That's because they're trying to do this. They're trying to fall sideways. And if they put their energy into going straight up, they don't have any momentum to keep them going that way. And they're going to come straight-ish down. The Earth's going to turn underneath them, but they don't get the benefit of the sideways fall. They need to be going sideways to be able to orbit, not just straight up. And so simple things like a weather rocket might go practically straight up. Might. Usually isn't, because they're still trying to put it into a particular place with that weather sensor. Because there are weather rockets. I don't know how much there are now, because now we have satellites. But it used to be we had actually launching from Michigan weather rockets that would launch from a base way up in the northern Upper Peninsula. And they would take weather recordings from up there and eventually come back down. But if you imagine this rocket going straight up and straight down, it's not a very useful rocket. What's more likely is it's going sideways in a direction. But his point was, this is what they're doing with these launches to orbit. They are bending them over to try to get them into a particular path. Now, when it does that, it ends up with some orbital plane, meaning as it circles around the Earth, it is following sort of a circle and back and forth and back and forth. Even though the Earth might be turning underneath, from its perspective, it's a ring. It's not up and down or something like that. It's in a ring. We call this the orbital plane. If you imagine every step in that orbit slicing through the center of the Earth, that's the orbital plane. Now, when it's doing this, these orbits are never round. Never. If it's a perfectly round orbit, you will crash. For various mathematical reasons, a perfectly round orbit isn't an orbit at all. There is what they call eccentricity. It's an ellipse, not round. Now, mathematicians will say, well, round is a special case of ellipse. Yes, it is, but you will never get that. What it actually is an orbit with some eccentricity, which is how far it is from round. So your typical planet has an eccentricity that looks so close to round that you would not be able to tell the difference with your eye. Even if you could go up in space and look down at the orbit and somebody magically drew it like on a slide presentation, you couldn't tell the difference from round. But it's not round. It is an ellipse with the center of one of the foci of the ellipse, basically the center, is very close to the center of the big body of the two. But if you've got two things that are very similar in size orbiting each other, the center may be between them because they are each of them bending around that center. Now, that in fact is always the case. When the Earth goes around the sun goes around the Earth. People who tell you that people used to believe that the sun orbited the Earth, how funny they are. It's like, well, as a practical matter, the Earth orbits the sun. But what really happens is there's some point, they call it the barycenter, which is somewhere close to the center of the sun, but it's not the center of the sun. The barycenter can be roughly calculated by knowing how big the two bodies are and how far apart they are. And it's going to be really close to the big body and really far from the small body. But if we're looking at two planets orbiting each other, which is an example that can happen, and they are close to the same size, their barycenter will be somewhere between them. So the orbital plane is what we call the sort of imaginary plane traced out by the planet or the smaller body orbiting around the larger body. There are three particular orbits that are important for near future science fiction, especially, but they can be in other kinds of science fiction as well. Low Earth orbit is an orbit which is low, close to the Earth. It is something that is generally orbiting the Earth in 90 seconds, or 90 minutes. 90 minutes, don't say 90 seconds. If it were orbiting 90 seconds, it'd be really low and running into things. But it is orbiting at 90 minutes around the world. It is small. It is easy for us to reach with current rocketry. Higher orbits and orbits going all the way to the moon takes a lot more energy, a lot more planning. Then we have geosynchronous orbits. I'm going to draw a distinction that don't get drawn often in science fiction, but I want to draw the distinction between geosynchronous and geostationary. Geosynchronous is at a distance, and the distances are there, 42,000 kilometers from the Earth's center or 35,000 from the surface, where the time it takes to orbit is exactly the time it takes Earth to spin around. So every 24 hours, you cross over the point where you left. Or pick any other point that you cross over. You cross over that same point every 24 hours. And it can be in any orbital plane. And so you might have a geosynchronous orbit, which is actually even going North Pole to South Pole. It costs a lot of energy to go in and things like that. Generally speaking, changing your orbital plane is expensive. But in theory, you could do a geosynchronous orbit that would orbit the Earth from the North Pole to the South and back every 24 hours. They do have polar orbits. I don't know what their period is, but they're probably closer to the 90 minutes. It's a great way of doing surveillance of whatever might be going on in areas of the world where we don't have a lot of people watching, but we can have satellites watching. But it can be any orbital plane. A geostationary orbit is a special geosynchronous, where the orbital plane is this ring around the Earth we call the equator. And that one never moves. As we look up in the sky at it, it is always in the same place. It is not ever moving from that part of the sky right there, which is really cool for communication satellites, because now I can send a beam up at it, and that beam will bounce off that and hit a receiving station somewhere, because it is a stationary target, hence the term geostationary. Now, what you can't have is a stationary orbit that doesn't move. And I'm sorry, Star Trek has done this multiple times. Unless you have essentially said, well, we've got so much power in our engines that we're not going to worry about real orbits. We're just going to call, anytime we're sitting someplace, we're going to call that an orbit. In our technology, you can't get away with that. If something stays in one spot, other than a geostationary orbit over the equator, if something sits in one spot, it falls. And so when Riker takes and positions the Enterprise in a stationary orbit over the planet's poles, it's like you took a stationary position. You did not take a stationary orbit. But the writers of Star Trek failed much science, so, and they still have made $10 billion, so it didn't matter to them. Let's talk a little bit about designing for free fall. Keep in mind, remember, every force matters. Small forces add up. Everything adds in. And so they have different kinds of engines. They'll have thrusters to push you ahead, and then they'll have attitude controllers to change where you're pointing, to change the definition of ahead. And they may have retro rockets, which are to push you backwards from the direction you're traveling. So those are part of the basic design. But when you're thinking about designing your ships, keep in mind where the forces are aligned. If that force is acting in a direction that passes through the center of your ship, then you're going to push in the direction of that force. If it doesn't line up with the center line, and hey, if you're writing a story, you don't have to get it mechanically, mathematically perfect, but you need the concept. If it doesn't match up with your center line, you are going to turn. In some way or another, you are going to turn. And you are typically going to experience one of what they call, all the way back in the airplane business, pitch, yaw, and roll. Pitch is your nose of your ship bends up or bends down. Yaw is that you have your ship is basically turning left or right, so to speak. And roll, you are spinning around your axis. Anytime you have an engine or a force that's acting not directly through the center line of your ship, it is going to cause some combination of pitch, yaw, and roll. Now, if the force is small, you might not feel it. But if the force is at all noticeable, you will not just get a push, you will get a change in direction. You might feel it. So when an enemy missile comes and hits your ship or even explodes near your ship is not just going to suffer damage, it is going to change course. And you will have to have computers or humans correcting course for this. Even you sitting outside and kicking the ship will cause some amount of pitch, yaw, or roll. Unless you're really good at kicking and you can kick right smack on the center line. When it gets down to designing habitats for free fall, things to keep in mind: there is absolutely no up and down. The concepts of up and down are gone away. And in fact, there's a certain amount of freedom because you can use that space that might have been overhead, and it's not anymore. It's now working space. If you look at the inside of an Apollo command module, it looks ridiculously tiny, but they moved around and worked in it because they could literally make use of the whole space. Apollo lunar module, same thing, that they had the ability to work whatever place they had to be. On the space station, they actually will put consoles and controls and instruments all around what you might think of looking at it as the ceiling and the floor, but it's all just surface. You don't have an up or down. What you do have to have is lots of grips and straps and even sleep sacks to keep you in place when you're moving around so that you don't go tumbling off into something, because small actions can potentially send you in big directions. Newton's laws are at play. When you're dealing with liquids or particulates, they end up everywhere. Everywhere. You need to have a way to stop them. Food designed for space is generally sticky because you don't want breadcrumbs getting into the expensive electronics because they can destroy things and you. Particulates. There's a classic old joke that happens to be wrong. It is a complete lie that somebody made up because they thought it sounded clever, about NASA spending $1 million to make a ballpoint pen that would work in space while the Soviets used a pencil. Well, first of all, NASA didn't design that space pen. The company, Fisher, I think, designed it and then sold it to them. And as soon as the Soviets had a chance, they bought it too, because pencils have graphite. Graphite needs sharpening. As you sharpen pencils, graphite goes everywhere in the ship, and graphite is an amazing conductor and can short out instruments. Well, lots of particulates can short out instruments. Lots of particulates can clog the air filter and so on. So your design has to make sure you have ways of not having liquids and particulates getting everywhere, and vacuums to catch them up. If you have food escape, which they love to do as a video to show off to the kids, of an astronaut chasing M&Ms through the space station and so on, it's all well and good, but you want to know where every one of those particles goes and vacuums it up essentially. You do need exercise. You need exercise. If you are in free fall, there is a tendency to lose bone mass and muscle mass if you don't find a way to exercise. But exercise, every time you move, you're pushing yourself away from something. So they've had to design exercise units with straps to actually hold you down. Showers need to be bags that keep all the water in, or you don't do showers, you do sponge baths. And even with sponge baths, where do the drips go? Your sanitary facilities, I am not going to get into the details of those because, for one thing, it's changed since I was a kid. But trust me, your bio wastes have to be vacuumed off into containment so that we don't have those going all through the system. You will design your habitat around compartments. For one reason, because that way if you have any sort of a vacuum issue, you can seal off the compartment with a leak. And also your compartments can have different amounts of radiation shielding. So your habitat design needs to keep in mind that things go all over the place if you're in free fall. And to get around, everything is about this concept we call delta V, which means change in velocity. Everything is about that. Newton's laws are in play here. So when your spacecraft is trying to rendezvous with, say, the space station, it gets really complicated because, and I've got a presentation coming up on orbits where we'll get into this more, but you can't just point at the station and say, I'm going there. You have to change your orbit gradually so that you're in the same orbit as what you're heading for, which means you have to do it only at a certain time. If you try it at the wrong time, you might reach the right orbit, but it's not there at that point. And then the rendezvous effort becomes a matter of now trying to narrowly close that gap. All the time as you're closing, your orbital height keeps changing, so you have to keep bumping it, but you don't want to intercept too fast, because a difference of 5 meters per second, which sounds on the scale of stuff out in space, sounds like not much, but 5 meters per second is a huge amount of miles per hour, and you are essentially looking at crashes of heavy equipment at 30, 40 miles per hour And so you need to very closely approach and watch the delta V and control the delta V. And if it's too fast, you may have to back off and try again on the next orbit or something like that. And departure is not quite as bad, but you still have to make sure that as you back away on a path and at a velocity that you're not going to collide with something. For instance, the International Space Station is actually pretty darn big, size of a football field, and it has some things going up and down. So when you depart, you have to make sure you are planned a course that is going to take you away, but not too fast where you lose control. You've got to get away before you can start seriously kicking in the engines. When you yourself go out in a mobility unit for an extravehicular activity, you will be likely tethered, or you might be on some sort of a mobility unit. You might be on the Canadarm, the arm that lets them move stuff around in space, but you might go untethered. And this is one that, unfortunately, is a real popular science fiction trope, and I think it's valid, but it gets exaggerated. I would happily go outside of the space station untethered briefly, because the space station and I are in the same orbit. And in bad science fiction, as soon as my tether is gone, I fall. No, I'm in orbit. It's in orbit. We're in roughly the same orbit. As long as there is a hand grip within reach of me, I should be safe for a little while. Give it time, I will start to drift a little bit because my orbit will never be exactly the same. But over time is different from a short period. For a short period, I might be safe in this. And so the other classic trope of science fiction is, oops, you dropped your wrench and the wrench flew away and you don't have your wrench to do your work, or you dropped the nuts or whatever. That's not actually what would happen, because the wrench and the nut are also in the same orbit as you. Now, what might very well happen is you panic and reach for the thing you dropped and bump it, and now it's heading off into space. In 2001, the astronaut that got killed by HAL got hit by the arm and went knocked flying, and all of a sudden, because 2001 got it right that he wasn't off wandering in space up until HAL hit him, and then off he goes. Untethered action is briefly not a danger, but you better be very careful what you do next, because you can push yourself farther away. If you don't have a tether or a mobility unit, you're not getting back. Inside the ship or the habitat, you need to learn new reflexes, and you will have to deal with space sickness for a while, although all research I've said says space sickness is a temporary thing that pretty much everybody gets over in time, but time might be a couple of days. Essentially, the little fluids in your inner ear that hit the little hairs to let you know where up is and where down is are really confused, because there is no up and there is no down. They're getting hit by fluid that just goes in random directions as you turn your head, and you don't know where it's going, and it causes a convulsive reaction in your digestive system. It can still happen even after you've been in space for a long time. If you move too suddenly in a new direction, you might still get nausea.
Just imagine when you float to the top of a pool, except without the water, and you move just slightly and the floor immediately becomes the ceiling. The entire room is changing perspective all the time. At first, it's really disorienting, and if you get going in one direction, it's hard to recover.
Really can't control where I'm going. Oh, sorry.
My job was just to not crash into the back of the plane.
I'm just surrendering.
So this is a science reporter who was doing a report on the Vomit Comet, which is not actually one plane. It is a description for the experience of being on planes that they can go and do parabolic loops that have a long stretch of time where you are in free fall. They're not turning off gravity. They're not in microgravity, but yourself and the plane and everyone in it and everything in it are all falling at the same speed. And what she went through is an example of what moving in free fall will be like until you get your space legs, so to speak. So rules you need to learn for working in free fall and learn fast. You need to be the sort of organized person that your mom and dad wanted you to be when you were a kid and you didn't understand why they cared so much. Put it away when you're done with it. Don't let go of it. Though again, if you let go of something for a brief period, it's going to stay in space around you exactly where you left it. Strap down whenever you can, because you may do things like twist a wrench and it will twist you. You can actually make your whole body shake by simply shaking your head, and your whole body will swivel the other direction. Plan everything. This is what's frustrating for people who want to watch things happening in the International Space Station and are in a hurry. They don't do anything without hours of planning, hours, to know exactly what they're going to do because they don't want the consequences of getting it wrong. And be aware of things around you. So if somebody does accidentally knock that wrench flying through the station, you're not getting hit in the back of the head with it. So that's free fall, and there are ways to get dead there, one of which is not being aware, and here comes that wrench to the back of the head, and wham, because you weren't aware of what was around you, you have the accident. Related to that, disorientation, possibly space sickness, especially for people who are relatively new to it. Just the concept of up and down being whatever direction somebody chooses it to be. That they look like they're sitting over there, but I think that they are hanging from the ceiling. That disorientation and the distraction can all get to you. The distraction of, this is so fun. Everything is so cool. This whole floating around in here, it's like wham, you run into something. Keep in mind Newton's laws of motion, which I've mentioned a couple times already. First law, inertia. Inertia. An object in motion stays in motion. An object at rest stays at rest. Unless it's acted upon, which is the second law. Then it keeps going in the new direction until something acts upon it. And also, again, for every action, equal and opposite reaction. And equal and opposite are mathematical. You really can push your ship with your muscle power. And the ship weighs 200,000 times what you weigh. Masses 200,000 times what you mass. Let's use proper physics terms. So if you manage to push that ship a millimeter, that ship is going to push you 200,000 millimeters. I think you're losing this battle. And again, keeping in mind, weight is not mass. When that great big massive object is coming at you and it's weightless, it can still squash you like a bug. So losing control of the things around you is a hazard, and losing contact. Yes, eventually, if you lose contact with your ship, you are going to eventually separate from completely and not be able to get back. There is a really, really cool short story, I think it might be a novelette, which you can actually still buy on Amazon, and it won't cost you much. And I think it's just so cool, but I have a big love for it. It's a story called Fighting Madness by P.J. Plogger, who was an excellent writer. He was an award-winning writer, and then that darn happened to get involved in computer programming and turn around and write some of the most influential computer programming books ever, and get all sorts of money as a programming consultant. And he hasn't done any science fiction since. This was back in the early mid 70s. And I sent him email one time and he said, yeah, I'd like to get back to science fiction, maybe when I retire. And it's like, whoa, okay, I thought I was a bit of a workaholic here. But Fighting Madness is a story which is a sequel actually to an award-winning story he wrote, where a physicist managed to come up with a magic equation and a magic reaction. The first story is okay, but it's not nearly as good as the sequel. But essentially, he managed to turn off all nuclear reactions in Earth space. Permanently off. Nobody knows how to turn them back on again except him. And he literally drives himself insane, so he can't do it. Fighting Madness is the sequel where he's out of the asylum, but he has more or less permanently burned out his math intuition. He can't understand his own math anymore. So he is looking for jobs for people who can do simple math, but they can't work at the level he was working at. And he ends up on a construction shack in orbit, helping to build a space station. And he is snooping into things that people don't want him snooping into. And he gets sabotaged by somebody who manages to send him tumbling off into space with no tether, no mobility unit, and he is lost. But he has his tools, he has the nuts and bolts he was supposed to be using to do his work on the station, and he has enough of a physics brain left that he can calculate angles and turn around and judge masses because he knows his tools. It's like, throw the wrench as hard as he can that way, which pushes him that way, and start throwing other tools and correcting his angles and throwing nuts and bolts to propel himself. And yes, he outmasses them by a lot, but he's accumulating inertia to drive himself back to the station. And I've just completely spoiled my favorite part of one of my favorite stories. That story right there is why I am a hard science fiction writer. That story that I read in like 1976 has stuck with me now for 50 years. Because it was all about how he used the science to save himself. It's still a fantastic story. Go buy it on Amazon. It's cheap. Okay. But now let's quickly talk about artificial gravity so we can get to the last one. One type of artificial gravity that we know will work, will not break any laws of physics, is a really big ship. If your ship is an asteroid, asteroids are a lot smaller than the Earth, so they have a lot less mass to apply, but they're also very small in radius. So that relatively speaking, you can experience close to 1 gravity standing on an asteroid. The tidal effects are going to be maybe not as dangerous as a black hole, but you're definitely going to have your feet pulled more than your head. It's also the idea of pushing around a small asteroid as your ship is a little bit expensive in terms of fuel. But technically, you could use an asteroid to generate enough local gravity that you would have quote-unquote artificial gravity. Another approach, simpler, is just constant thrust. Because one of the things Einstein showed us is there is really no difference between forces. Between gravity pulling you, which of course we now know isn't really a force, but there's really no measurable difference between gravity pulling you and something pushing your feet. That a ship that is pushing you up fast enough with enough force feels just like gravity. The problem is keeping that force going. It's going to be expensive in terms of fuel to keep that up. When we launch rockets today, they have a brief period where it's many, many, many gravities you're going through. But then they use up all their fuel and it doesn't last. So unless you come up with some new form of propulsion, constant thrust is not a successful way of generating artificial gravity. Plus, it means you move through space. So you're not going to generate artificial gravity with constant thrust while you are sitting in orbit. And the last one is spin. If you've ever been on a merry-go-round, if you've ever been on one of those rotor rides at the carnival, if you've ever taken a bucket of water and spun it around over your head, or anything like that, you understand the idea of spin gravity. It is the centripetal force. You'll hear it called centrifugal, but there's a difference. Centrifugal is the force of the thing moving around. Centripetal is the force of whatever's holding you from flying off. So centripetal force is your bottom of your bucket holding the water as you spin it over your head, keeping the water in place so it doesn't fly off. And that is just spin gravity. It feels sort of like gravity. We'll talk about a few of the differences, but it's just gravity-like. But it has these limits. First, it takes some energy to get it going, and then if you had to stop, it takes some energy to stop it. You don't get the water just hanging there in the bucket. You have to use your muscles to make it move, or they have to drive the merry-go-round or whatever. It takes force to get it in motion, and then things get a little weird. One is this picture here. Oh, come on, play it again. Play it again, come on. Let's do it this way. Watch carefully. Watch the ball moving in a straight line from your perspective. If you're the person outside watching, it's going in a straight line. But if a person's standing on the red spot, notice that it looks like it curves. That it is curving away behind the spin. This is an effect that can cause small, interesting changes in your story. They aren't really rotating, but you feel like they're rotating, so it befuddles your instincts. If you try to shoot a bullet at somebody, bullet might be fast enough so you don't notice. Toss a baseball, you're probably going to notice. And even something as simple as pouring a drink, as that drink is falling from the pitcher towards your glass is moving. And it's going to look to you like the water is curving. And so you have to learn new instincts to be able to do something as simple as fill a glass, or you don't try to fill it from a pitcher, you fill it from a hose. So the Coriolis effect is going to befuddle your instincts. And differential acceleration, it's sort of in the same concept as tidal forces with your feet at a different acceleration than your head, but it's not, but it's kind of. Because if you are standing on this rotating platform, your feet are rotating faster than your head. And in fact, your feet might be moving and your head not moving at all if it's a small place. And so this can A, be confusing, B, it can be lethal. They call it the water hammer. And this is by no means the only place where a water hammer happens. A water hammer is an effect that often happens in pipes where changes in water pressure can cause water in parts of the pipe path to sort of oscillate back and forth, because you've got water moving fast in one place and slow in another, and there end up being gaps in between. And so you hear about water hammers in some cases in different industrial projects and so on. Now imagine that is going on in your bloodstream, in your skull. And the blood flow in your head is stopping and starting and stopping and starting and stopping and starting. We call that strokes. Very small strokes. We call that strokes. And it can potentially even cause worse. It can cause not just blood stoppage, it can cause lesions, hemorrhagic strokes. Those are the bad ones. I've had the ischemic stroke. It's no fun. Hemorrhagic is your brain bleeding. So you have to be very careful of the water hammer effect, depending on how fast you're spinning and how big things are. And also from the outside. Imagine you are clinging for some reason to the outside of your ship. that maybe you've just now got back after throwing your wrenches and your nuts away and you've grabbed the outside, you're still hanging on for dear life because the whole thing is spinning. And if you let go, now you get the centrifugal force, which is basically has been tossed you off away. So if you're trying to do realistic spin gravity, I recommend SpinCalc. Cool website, which will let you say, my ship is this big around, and I want it to spin this many times per minute or whatever range. How much gravity will they feel, and will it be dangerous? Will there be a chance of a water hammer effect or nausea or so on? SpinCalc, it's a free calculator, and it has changed the design of my ships in my stories because I knew what speed I wanted the ship to travel, and I knew I wanted to be absolutely safe. And that's when it came up to be, okay, then your ship is going to have a 60-meter radius. Okay. And I designed my whole ship to give me a 60-meter radius so that I could write one scene where the ship was rotating at a particular speed and Earth came in and out of sight in the viewport every twice a minute. Because SpinCalc told me for that's what I needed. If I wanted to have a quarter gravity and Earth showing up at twice a minute, this is how big things have to be. And you can just play back and forth with that. Designing your ship for spin, or your station for spin gravity, there's a couple of different common approaches. One is you have just your ship as a rotating cylinder. It spins around its central axis, and that's the speed that it goes so that you have your spin gravity. You might not have the whole ship spinning. You might have a ring or a disc. The mechanics of this gets interesting because now you have to have a way, presumably, to be able to enter and leave the ring or the disc from the center. It's much more likely that you'd have a rotating center as well, but you're going to have to decide which way you want to do that. An interesting approach, which works for smaller ships, is just the tether. Imagine a ship that starts out as a big capsule. And once it's out in interplanetary space, the two capsules separate and they're joined by a tether. And now they start spinning around on that tether. And that tether might actually be a tunnel that you can climb up and down in. Keep in mind that as you climb up, it actually, the spin gravity goes down. And as you climb back down, it goes up. So the tether design is an interesting approach. That is, in fact, the approach they use in, now I've lost it, the movie Europa. And so that is another approach, which takes a lot less stuff than building a big ring or a big disc. Big ring and big disc take a lot of material and a lot of time and expense to build. Also keep in mind that the mass distribution affects things, that mass distribution affects your rotation. So suppose we have a giant ring is our space station, and then for some reason everybody's throwing a big party and all 200 people aboard the ring all get together for a party on one side of the ring. The ring's now going to be lopsided. And unless you have correction engines that are accommodating this, you're going to actually have your ship start to go into a massive distorted spin. It's going to be ugly. Also keep in mind how you rendezvous with and depart from the station or the ship. Relatively speaking, your center, even if your center is rotating, it's very slow in terms of feet per second or meters per second. It is very slow, even if though it's rotating at the same speed as the outer edge is just a bigger place. And so it can be very fast on the edge. So your rendezvous and departure, either they're going to be taking place through the central core, or we're going to have really good pilots who are really good at catching something in motion. And when they do, remember that business about mass distribution. If a really big ship rendezvous with the outer ring somehow, your ring is now going to be way off balance. So you're probably most of the time going to be rendezvousing through the central core. And that basically is what we have. I am going to be, if you look at the schedule, I am going to be talking more about orbits late November. Coming up next week is going to be marketing for introverts. On the 2nd, we'll be learning from improv. Whose story is it anyway? In the 9th, we'll be talking about openings. On the 16th, we'll be talking about story strategies. Then we get to our orbits and transfers. Ending up November with a tribute to one of my absolute favorite authors and friends, Jack McDevitt. On the 7th, I'll be talking about copyright. On the 14th, I'll be talking about voices. 21st and 28th, I will be doing some of my mystery workshops. Questions on anything here with spin gravity and free fall?
I'm going to go back through the video slower and go over the math again. But an easy question for you to answer is that short story. Could you put the name of it in the chat, the one you recommended?
Sure. Let me stop share so I can get to the chat.
And just so you know, I actually like the math, so I wasn't annoyed.
Not annoyed, but it's a lot to process. I'm going to
Yeah,
go
that's why
over the
I'm-
video again.
Yeah, and that's why I like that he records these so we can do it again.
So Fighting Madness by PJ Plogger. Again, Plogger was one of the early authors on software design in the early age of Unix and the C language, has been a phenomenal influence on our careers as programmers. Even if we don't know him, he's been an influence. And it was really a surprise to me when I found out he was the author of this, because I had remembered this story since I was like 12 years old. And then to see his name on it, it's like, Plogger, you're kidding me. And so I sent him an email and about it. Also, that first appeared in a trade paperback called Analog Annual. It was an annual anthology from Analog, not of stories that had been in the magazine, but of stories by their authors, some of their better authors. And the original one that this was a sequel to was an award-winning story in Analog, and then he put this out, and then they never had a second edition of the annual. But that was where I read this, and later on, I had an opportunity at the International Space Development Conference, which is where Baen Books puts out their, or hands out their award for the Baen Memorial Contest every year, is at this particular conference. And the same time I was there and giving a chance, not as a winner, I was second place, but the winner asked me to give his speech because he couldn't make it all the way from New Zealand, and got to have lunch with Buzz Aldrin, which is why I owe the winner, RPL Johnson, I owe him lots of beer. But it was also, they were giving a Lifetime Achievement Award to Ben Bova, who was the editor for Analog at the time and the editor for Analog Annual. So I've never had a chance to meet Plogger, but my copy of Analog Annual has Ben Bova's signature. And he had the same reaction I did. I wish Plogger would write some more. So I think he's published like 4 short stories on Amazon. All of them are okay. This one was a life-changing story for me. Almost everything I want in my writing career started with this story. So, other questions? All right, then I will call it a day and stop recording.